Thank you so much. Let me grab this. I like to wander when I'm talking. So before I get started, can you all hear me? Is this working well? Yeah, awesome. So I'm what my friend Brian likes to call an overrepresented person in technology. I'm a cishet white dude, old. If, as we go through this, you're not overrepresented and some of this stuff isn't clicking for you and you want to go deeper, please reach out to me. I'm happy to make the time. I just want to put that offer out there before we actually get started. All right, so this talk, I'm titled Kubernetes as a Platform. I think another alternate title might be why I'm still excited about Kubernetes. So we're like 5 years into Kubernetes. That's a long time to do anything. I'm kind of exhausted by it. I know you are too. But hopefully this is actually will help, bring some depth and actually look at it in an interesting new light. All right, so a little bit about me. I'm a platform builder. I started my career at Microsoft. I've actually been up in Seattle my entire career and working on the Internet Explorer project. And you can boo me if you want. And the fascinating thing starting your career at Microsoft, and wherever you start your career, oftentimes that's sort of like you imprint on a lot of the values of that company. And say what you will about Microsoft, they are through and through a platform company. I mean, I can get up here and bounce around and say developers, but Steve was right? It really is about developers, and Microsoft feels that in their bones, and that really imprinted on me early. So a lot of what I've done through my career is really about platforms. And so for me, a good platform is something that enables people to be more productive. It raises the toolkit that they have to work with, and it allows them to do things with your platform that you couldn't imagine when you actually created it. And I think that's one of the most sort of satisfying and exciting things about working on infrastructure, things like this. So I was at Microsoft for about 7.5 years and then doing client-side stuff. And then I'm like, I want to figure out how this stuff works on the server. And so I joined this little company called Google up in Seattle. We had like 4 or 5 people up in Seattle at the time. And this was 2004, right around the IPO. And I'm like, well, if I'm going to figure out how stuff works on the server side, Microsoft's not the place. Google probably has this stuff figured out. So I joined and immediately started writing client software. Because Google at the time, like you show up and they're just like, hey, work on this. I think they're a little bit better about it now. But over time, I actually did move towards doing stuff server side at Google. And again, that imprinted on me. And so Google does not run stuff server side and manage infrastructure the way that the rest of the world does. And so I was sort of twisted in my sort of learning how to do stuff on that side of the wire. And it only later did I actually figure out sort of how things work in the real world. But Google runs this system called Borg. You've probably heard about it. Over the course of 10 years, they essentially found a way to use every single ounce of performance and capacity out of the computers in their data center. The primary driver for Google for a lot of these systems ends up being one of efficiency. When you're running that many machines, a single-digit increase in efficiency actually turns into real money. And so a lot of the focus was there, combining the, early Google was all about search, and search was essentially 2 processes. There was a crawling and indexing process, which was largely batch, and then there was a serving process, which was low latency. And so a big part of Borg and the infrastructure that was built was really aimed at sort of bringing those things together into one compute platform to use every single piece of the computer. Along the way, though, the abstraction that developers at Google used to run stuff in production changed. It moved from being managing servers to managing abstract processes that are scheduled by a system. There's definitely echoes of HPC systems. This stuff goes back a long time sharing, that type of thing. But the birth of this, with this really was the birth of a lot of the core technologies that are Linux containers today. And so Google spent the time putting the C group technology into the Linux kernel, which is sort of about like half of the core kernel features that make containers work. And it worked really, really well. And so when I was at Google, I did a bunch of stuff. I did some Google Talk, I did some ad stuff, and then finally we did cloud things. And I started Google Compute Engine while at Google, which was really about how do we actually bring something that's familiar to the rest of the world to Google, VMs, because Google generally didn't run VMs at that time. But then we wanted to bring the developer experience that Googlers had closer to the developer experience that the rest of the world had. And so that meant either having everybody at Google start rewriting stuff on raw VMs or bring a Borg-like experience to the rest of the world. And that really was the genesis of Kubernetes. Along the way, you know, Google doesn't work like the rest of the world, so we had to change, we had to adapt, we had to listen. We brought in early partners like Red Hat through OpenShift, and it was, you know, really, really exciting to actually see the merging of these ideas, the stuff that had been proven at Google, along with the needs of the real world. All right, so what is Kubernetes? You all have probably heard about it. At sort of the most practical level, Kubernetes is a way to take a process, package up everything that process needs into a container image, and then give it to Kubernetes, and it decides which computer to run that thing on. And once you get that dynamism of running a bunch of things across a bunch of computers, that creates some new problems. And some of those problems are things like, how do you find those things? How do you communicate between those things? How do you do load balancing? How do you handle storage? And so Kubernetes starts with that dynamism of dynamic workload placement, and then does the necessary things to be able to fill in the rest of the gaps and start solving the rest of the problems that creates. Okay, but what is Kubernetes really? Kubernetes is a database. I bet you didn't see that coming. It's really a database with a policy layer in front of it with a bunch of control loops that actually work against that database. And one of the fascinating things that emerged out of this is that the patterns that we use to solve that problem around workload placement and communication and replication and the things that sort of are part and parcel of Kubernetes, those patterns ended up being useful for so much more. And so one of the things that I'm going to really go in deep here is about how are the core patterns for how Kubernetes does what it does, what are some of the sort of design philosophies that we have there, and then how did we create these extension points so that we can make these usable in more contexts. And so that's what I think is really exciting here. All right, so here is some beautiful artwork that I drew. All right, so at the center of Kubernetes is, really, I got a laser pointer, check it out, is the etcd, which is a database. Now this is an interesting database. It's actually, if you trace the lineage, it goes back to this thing at Google called Chubby, horrible name for a system. And that there was a paper written on it that inspired things like Zookeeper. So it's in that same class of databases, oftentimes called a lock server, highly consistent database there. Whether or not that's the right database for Kubernetes to have used, I think you could argue that. There's some interesting features that actually come out of etcd in this class of databases that I'm going to get to in a little bit that are critical for the way that Kubernetes works. The only thing that talks to etcd is this creatively named server called the API server. And so the API server is essentially a policy agent in front of the database. So the database is a raw database. The API server essentially takes different schemas, exposes them to the world, implements a lot of the sort of API gateway management-y type of things that you want to do on top of that. Things like permissions, things like authentication. So that's primarily what that API server does. There is some sort of Kubernetes in the API server. You know, these abstractions are not as sort of clean as we'd like them to be. That's one of the things that the community is going to be working on in the future, is to actually sort of take this part here and turn this into sort of what some folks have been calling sort of a universal control plane that is not specific to Kubernetes. And so I think that's an exciting future direction that we're going to see happening here. So then there's these other processes that we call the scheduler and the controller manager. So the scheduler is the thing that actually does the bin packing of which container is going to run on which machine. It's interesting that it's called scheduler, because we usually think about scheduler as like a time thing, but this is actually a space scheduler. So it's the placement engine. And then there's this sort of kitchen sink thing called the controller manager, which does a lot of the sort of, you know, background processes to be able to make Kubernetes do its container thing. And then finally, on each of the worker nodes, we have this server called the kubelet. It's essentially the agent. And it sort of fronts Docker or the container runtime, whatever one you're actually talking to. So it's the thing that actually runs the actual containers for you. Naming here, kubelet is a Googleism. In Borg, we had the Borg master and the Borglet. The successor system to Borg was called Omega, so there was the Omega master, and then there was the omelet. It's a really bad joke. It's really bad. All right, so I use the term controller here, and I think this is really fascinating because this is essentially the core distributed system primitive in Kubernetes, and it may be a little bit different from some of the stuff that you might have dealt with in other contexts. The whole goal of this is essentially reconciliation over time. Kubernetes, by and large, when you look at sort of the overarching control patterns, does not have state machines. Instead, what you have is you have these componentized systems where you actually tell Kubernetes, here's my desired state. Here's what I want you to make true. And then it's up to a controller to look at the real world, look at the desired state, and try and make some forward progress. So it's sort of a greedy algorithm in terms of relentless forward progress. How do I actually say, here's what the user wants, and it could be the user or it could be some other system because we layer these things on top of each other. Here's what the user wants. Here's what the real world is. Let me try and converge these things over time. Now, this is a really, really resilient distributed systems pattern because if the controller crashes and loses all its state, it can wake up and actually discover all of that. It can start over, and that question of what does the user want, what is the real world, let me try and converge these things, that is actually really resilient if things crash, if you have these things fighting against each other, if you have bugs, this thing ends up being very stable. The other thing that's really nice about this is that it's really good at dealing unexpected situations. When you build these big, complicated state machines, oftentimes your state machines really don't take into account some of the failure modes that you really should be thinking about. And so a lot of, over time, a lot of the sort of debugging and hardening of these types of things is understanding more and more of the different failure modes, adding states to be able to deal with those, with recovery, all that type of thing. With this controller model, if you find something that you didn't expect, well, that's just a reality that you have to deal with, and you still make that forward progress towards where you want to go. All right, so this is a picture of me and my family after hiking out of the Grand Canyon. And the Grand Canyon, if you've ever hiked it, is fascinating because they say that down is optional and up is mandatory. And so, you take a couple of kids down to the bottom and then you sort of push them back up. It was fun, and this is at the top, But like along the way, your job is, there's very much this one foot in front of the other, relentless forward progress. The kids are sitting here going, my desired state is to be at the top with ice cream. My current state is I'm not at the top. What do I do to actually get myself closer than that? And so they're very much at this sort of primitive, sort of, primal, sort of like, okay, I just want to actually get from here to there. And that's my example of a controller there in real life. So here's a sequence diagram of how these things interact and layer on top of each other. And so sequence diagrams are objectively the best diagrams for engineers. I love these types of things. So the way that this stuff works is that the user here creates a pod, and for all intents and purposes, replace pod with container, writes that into the API server, and the API server writes into etcd. So this is essentially writing in, here's my desired state of what I want. And then the scheduler actually gets notified, hey, there's a new pod that hasn't been assigned to a machine. It then goes through, figures out which machine it wants to run that on, binds that pod to the worker, and then writes that back into etcd and then returns. And so you can see that at no point does the user actually talk to the scheduler directly, right? The API server doesn't actually really reach out to the scheduler. I'll describe what I mean here by watch. And then finally, there's the kubelet, the actual node. It actually says, oh, I have a new pod that's been assigned to me. It says it should be running, it's not running. Let me go ahead and fix that. It then goes through and essentially calls Docker run. Oop, my machine went to sleep or something here. What happened? Let me try and plug and unplug. See if we can get this going. Oh. Maybe. Let's see, is it going? Okay, there we go. Sorry about that. right? So this thing essentially calls Docker run and then updates the status as sort of like, because this could take a while and there might be intermediate states like pulling images and stuff like that. So the fascinating thing is that these things layer on top of each other. They don't communicate directly. All of the different signals that they get are through this sort of controller model intermediated through the API server and the fundamental database. All right, so that watch term that I used there, and so like in distributed systems, that's sort of like how does one component find out about something else often becomes a really, really hard problem. I mean, this is, you know, Kafka, right? So the way that this works is that there's a quality of databases like etcd, like Zookeeper, like Chubby, where you can subscribe in a lightweight way to say, hey, when any of these particular items in the database change, let me know right away. And so that's called a watch. It's different than a subscription in like a pub subsystem because the watch is not stateful. It's actually based on the underlying connection. If your connection drops, then the server's like, oh well. And so the next time you reboot or you reconnect, you have to essentially do a resync going like, I don't know what happened in the immediate time. All I care about is what is the current state of the database, not the events that happened in between. And so this is a big place where watch systems differ from event systems. In event systems, oftentimes, you'll get all the intermediate events. You may care about the end state, but you'll actually get the blow-by-blow as it goes. With Kubernetes, you could have a controller sleep for 15 minutes, come back up. It doesn't care what happened in those intervening 15 minutes. All it cares about is what is the desired state now, what is the reality, how can I make relentless forward progress towards converging those things. And so this is what we call sort of a level triggered system, because you're actually based on sort of what is the state versus an edge trigger system, which is you're based on events. And so it's a bit of a twist from sort of the event-based distributed systems that I think a lot of folks are building at the application space. All right, so a lot of times we talk about Kubernetes and the class of systems that we're talking about here as container orchestration. And orchestration to me implies that you have a plan, that there's some big score and everybody has their part to play and it's all planned out beforehand. State machines are kind of orchestration. But with Kubernetes, with these controllers reacting against each other and working with each other, it really is, it's more like jazz improv than an orchestra. So like, let's say that you're an orchestra performance and the fire alarm goes off. You know, people probably exit calmly, you know, put down their champagne, right? They leave, right? And it very much interrupts that performance. Now, if you're at a jazz improv performance and the fire alarm goes off, it's just as likely that the performers will work it into the music. They'll actually work with it, they'll roll with it, they'll actually deal with those unexpected situations. And I think that's one of the really interesting qualities of this type of distributed system. All right, so that's the core of how Kubernetes works. One of the things as we built it that comes through is what we like to call sort of a UNIX philosophy. Kubernetes introduces a lot of concepts. These concepts are granular. It's a lot for folks to wrap their heads around and oftentimes can actually be a barrier for folks understanding the system. But those concepts are relatively small, scoped, and reusable and layerable. And so just like when you're learning Unix and there's a command line and you find that I have all these primitives that I can put together to do unexpected things, that's how we wanted to build Kubernetes. We wanted to have a bunch of primitives, a toolbox that you can use, that you can put together to both do common things, but also to do the unexpected things. What it means is that sometimes the common things are not as straightforward, as easy as you might like, but you know, through the fullness of time, we think that it's really gonna, these primitives are gonna actually sort of last and be reusable in new ways. All right, so, let's see, there we go. Okay, so the core primitive I talked about here is a pod. So a pod is essentially a footprint, a resource footprint on a physical machine, or you know, one of the worker nodes. Could be a virtual machine, I guess. It includes a set of containers. These containers can actually work together in concert in a sort of tightly coupled way. And so this paves the way for things like sidecars and service meshes and a lot of the sort of, you know, more advanced deployments that Kubernetes enables. It also includes network configuration for that set of containers along with storage requirements and how that storage gets mapped into each of those containers. So that's the core primitive that the kubelet understands, and that's the thing that we're talking about as we schedule these things. Now, on top of that, we build a controller that we call a replica set. And this is where we see that sort of desired state really come into play. The replica set is actually fairly simple. It has a replica count, and it has a template for creating a new pod. And what it does is it reaches out and it says, well, how many pods do I have that actually match this pattern? There's this label query system that comes in there also. How many pods do I have that match this pattern? If it's less than the replica count, the desired state, then I'm going to create new using the template. Just stamp out new ones. If there's too many, then I'm going to actually go through and find some of those pods that are in excess and actually kill them and delete them and destroy them. And so it's a very simple thing to really reason about. The replica set wakes up, looks to see how many pods are out there, looks to see how many pods it should have, and then takes some action to be able to make forward progress. Now, what this means is that if you start out and you have a replica set and you're running sort of, some sort of like web server or application server, and you put in 100 as the number of replicas. And the system's like, okay, 100, I'm on it, boss, right? It goes through, it starts creating pods, and let's say it gets to like 50 pods. Right, because it may over time, maybe there's a limit to how fast it actually moves. That we put some dampening in the system to make sure that it doesn't, it doesn't actually sort of swing back and forth like somebody learning to drive stick. And so, like, let's say that you've gotten to like 50 pods, and then you change your mind. You're like, oh, I didn't mean 100, I meant 10. And a lot of sort of state machine-like systems, you might actually have to go through and complete that first operation to go to 100 before you actually go through and actually go back down to 10. In this sort of controller pattern, you can be at 50, and then the controller wakes up, and it doesn't know that you canceled or changed your mind or whatever. All it knows is that, like, I have 50, you want 10, let me go ahead and start killing some of them. And so that's where, you can be reactive to unexpected changes. That's sort of the jazz improv type of feel and play. So the replica set is very simple. It doesn't understand about versions. And so when you want to deploy a new application, oftentimes you want to make sure that you're responsible about upgrading versions, and you want to kill your old versions and roll out your new versions. On top of that, we layer this thing called a deployment. It does a rolling update. Essentially manages a set of replica sets. Just like replica set manages pods, the deployment manages replica sets. It brings up a replica set for the new version. It has a replica set for the old version, and then it actually changes the number of replicas over time to actually be able to spin up the new version and spin down the old version. And in doing so, it does a rolling update of all your processes. Kubernetes does not have a built-in way to do something like blue-green deployments, but using some of the extension mechanisms that I'm going to be talking about, you could build that yourself. All right, so that's all for like server workloads, this sort of like I want to bring something up and I want to keep it running forever. We can also do this for batch workloads. So we have job, which actually creates a pod and actually runs that pod to completion. And then on top of that, we have cron job, which actually launches a job based on a template, based on a time schedule. So you can see we're reusing some of those pod primitives as we go. All right, so that's all fine and good for the built-in things. Now this is where things get really, really exciting. Kubernetes has a bunch of built-in schemas and built-in controllers. Several versions ago, and these things have just really hit GA with Kubernetes, we introduced this concept of what would become custom resource definitions. This is essentially taking that database, adding new schemas, adding new API types, so that now, if you're like, okay, I like the deployment idea, but I want to do something slightly different, now you can create a blue-green deployment using these custom resource definitions. So you can take the control patterns that work for Kubernetes, work for the built-in stuff, and you can extend it into domains that Kubernetes didn't think about. And so that's really exciting, because we recognize that there's going to be these types of control patterns that folks are going to want to do that we're not going to be able to do everything. And some of the stuff we're going to do, we're going to get wrong. So we wanted to make sure that we created these extensibility mechanisms so that people could take these ideas and run with them. So that introduces this term operator that you may or may not have heard of. So I'm talking about operator as in a piece of code, not operator as in a person. When I first heard about this, I was a little confused, but then when it clicked, I'm like, oh yeah, computers used to be people too. The idea here is that an operator is a type of controller. This is my definition of operator. It's a type of controller that has domain-specific knowledge for managing a specific kind of system. And so instead of creating a generic controller for doing blue-green deployment, let's create a controller that knows how to actually do a HA deployment of, say, MySQL or Postgres. right? So now this operator has domain knowledge for how to actually deploy MySQL. If something dies unexpectedly, knows how to take those sort of operational runbooks, renders that into code, and actually drives that process automatically. Something like RDS running on AWS, in my mind, is an operator, right? What did Amazon do? They took a bunch of code, they took a bunch of operational best practices, they rendered those into code, and they put it behind an API so that it was automatic. This democratizes that so that anybody can use Kubernetes and the Kubernetes control plane concepts to be able to create these self-managing systems that are sort of in the vein of something like RDS. And we're starting to see an explosion of these things. Things like Confluent has a commercial Kafka operator, for example. And there's a bunch of community operators. Red Hat just released I believe it was a Postgres operator into the CNCF as a sandbox project. So we're starting to see these cases where these Kubernetes control patterns are being used to do more than just generic application workloads, but also create self-managing systems. And I predict that over time we're going to see applications that have sort of built-in operators. They wake up and go, oh, I'm running on Kubernetes. I know how to actually use signals from this system and interact with the Kubernetes control plane so that I myself can be self-managing as an application. So there's a fly in the ointment here. Making these controllers, making these operators is a big pain in the butt. They're not easy to write. And so one of the sort of bleeding edge things that we're working on right now in the community is exploring new ways to make these things easier to write, making this stuff be more accessible to more people. And we made a lot of progress. We still have a lot of progress to go. There's one example, it's sort of been, hasn't been driven super hard recently, called MetaController from this engineer at Google, that essentially lets you write one of those blue-green controllers that I mentioned in something like 125 lines of JavaScript. And so taking common patterns, making these things more accessible so that everybody can start using these distributed system primitives, using these patterns to be able to do more and more control. And then finally, like everything that we're talking about so far actually ends with launching and managing a pod, an actual container workload. But these control patterns are useful for more than just managing things on Kubernetes. We've seen folks manage other types of systems like, say, a networking system or a load balancer system. So if you think about like a centrally controlled load balancer, something like Nginx, you have a config file. Managing that config file is actually kind of a pain in the butt. And if you have to manage that config file across a bunch of different teams, what often happens is you have like the one or two people whose job it is to manage that config file, and you have to file a ticket or send them email every time you want that thing updated. As you start scaling this up to larger organizations, that really doesn't work well. And so one of the things that we see folks doing is using Kubernetes such that all of the different snippets of config that may end up in your, say, Nginx config, put those in as Kubernetes objects, and then have a controller that watches for those changes, looks at the state of the actual config for your Nginx, and then goes ahead and pushes and updates that. So we can start reusing these patterns for configuring more than just pods. We can use them for configuring network, for configuring storage, or for configuring larger business processes. I've talked to companies that are using this pattern so that they actually have one of these custom resource definitions that represents a team and an application. And they have controllers that say, well, for every application I need a Slack channel, I need a GitHub repo, I need a CI/CD pipeline. And they go through and they run these controllers, and these controllers reach out to other APIs to automate creation and maintenance of those different systems. And so that way, if somebody is like, disgruntled and deletes their Slack channel, this thing will automatically recognize, I should have a Slack channel. There's no Slack channel. Let me go ahead and recreate that for you and actually add all the members and keep it up to date. So it's that reconciliation loop. I think, continuous Terraform is another way to think about some of this. And so that, I think, is really, for me, the exciting thing about Kubernetes as we look into the future. It's really about taking these things that have these ideas around distributed control, some of the core concepts for being able to run this stuff, and then creating that universal control plane, creating that platform that lets you build higher level abstractions that capture a lot of the operational knowledge, a lot of those patterns, make those things more accessible. And so the core stuff that is part of Kubernetes right now, I predict that over time this will fade to the background, right? Like, how many people actually know the latest version of Linux that is like released and stable, right? Like, people, I'm sure there's some, but you all recognize that that's not where the action is right now. Linux is foundational, but it's faded to the background, right? People are really worried about other stuff. And I think that's the success of good infrastructure, is that it fades to the background, it helps shape the way we approach problems, and fundamentally it becomes boring. And so our goal with Kubernetes right now is to get it to the point where it's boring, but then it's also something that is boring in a good way, in that it's something solid that you can build on. We're not there yet, but we're still, I think, making good progress. So with that, I think I'm out of time. I think I hit it pretty good, right? Yeah, all right. But I'll be hanging out a little bit if folks want to discuss some of this stuff later. Thank you so much.